So today I'm going to cover what you need to solve finite volume problems in 2D. Okay. I'm also going to start talking about system of conservation laws and how to do the equivalence, or actually how to do the equivalence of a good enough scheme for system of conservation laws. And with how to solve problems in 2D and how to deal with system of conservation laws, you can start implementing first order schemes for Euler equations, which is first part of the project. And also we studied reconstruction yesterday, right? Reconstruction is basically looking at the interface and using the information from the adjacent cell, from the next cell over, to extrapolate to construct a second order approximation of what is the value of the variable on the left and immediately on the left and immediately on the right of the interface. So that gives you in combination with the good enough scheme, it gives you second order approximations. So just to have a refresher, so let's say this is I plus half the interface. The good enough scheme, previously our first order good enough scheme is to compute a flux of, let's say, good enough. That is a function of u bar I and u bar I plus 1. So this is the first order. All right. This is the interface flux of our first order. And when we go to second order, let me use a different color to represent second order. Actually, green. I'm going to exactly apply the same good enough scheme, but to the reconstructed ui plus 1 L and ui plus half L and ui plus half R. And the ui plus half L and R is reconstructed from the cell one more cell over. So particularly, I'm basically treating the cell averages as the cell center values, which we proved last lecture. It is a second order approximation. And then make a linear line and extrapolate to this point. So this value is going to be ui I plus half L. Similarly, I'm going to look at the cell center values, which is second order approximation of the volume average, and extrapolate to here, and this is ui plus half R. You can use exactly the same reconstruction for system of conservation laws, except for instead of only reconstructing one variable, you're going to be reconstructing several variables. And in the project, you need to reconstruct 3 variables: the density, momentum, and energy. All right. And for each variable, we do exactly the same reconstruction. So what you need to do differently is the interface flux. And for scalar conservation laws, we use the good enough flux, which we have 2 cases. One case is UL greater than UR. One case is UL less than UR. And we take the maximum and minimum of the flux within that interval respectively. And we are going to be talking about how to do this for system of conservation laws a little bit later. Okay, but before we go there, let's start to discuss about conservation laws in 2D. That's what we need to do. So conservation laws in 2D are represented by partial u, partial t, plus a partial f x as a function of u partial x, plus partial fy of u partial y equal to 0. All right. And fx and fy are the flux in x and y directions respectively. And if you don't have a y derivative, fy is simply equal to 0. We can also write f as a vector as fx and fy. Now it is a vector, and this can be, the same conservation law can be written in the divergence form, f vector of u equal to 0. So that's the conservative form of the differential equation. We are talking about finite volume here. So in finite volume, how should we convert the differential equation so that we can apply finite volume? What form should we apply finite volume to? Integral form. So how can we convert this into an integral form? We take the integral of this differential equation over a control volume, right? In this case is dx dy, right? We are integrating over volume. Okay, and the control volume can be anything. In our project, the control volume looks like that. All right, it's kind of a trapezoid. Now, if we integrate the first term, we get a d dt. This is my omega d dt of integration omega u dx dy. That's the total amount of stuff within the control volume. The second term, we're integrating a divergence. Now we use divergence theorem to convert that into an integral over the boundary of the control volume. And instead of a divergence, we have the normal, surface normal of this control volume dot with f of u over ds. And ds is integral, a line integral around the control volume. And of course, if the control volume has 4 sides, you can split this boundary integral into 4 integrals along each line. All right. Okay, so this is equal to 0. And in particular, if omega looks like this, we have d dt. The integral can be written as the volume of this cell, the volume of omega times u bar, right? Let me say just this is omega I, the ith control volume. Then the vi is I should be talking about ai, because ai is no. Let me say vi. Vi is kind of the volume of this control volume, and the u bar I is the average in that control volume, right? Okay, now this term, as I said, it's split into 4 integrals. And these UI bars are what we keep in finite volume scheme, is what we store in the computer and what we evolve as a function of time. The flux at the interfaces, or more precisely, the boundary integral of the flux at the interfaces is what we need to approximate. Okay, so we are going to be summing j goes from 1 to 4 for that particular case. If it's a triangular control volume, it's actually j goes from 1 to 3. If it's a hexagonal control volume, it's j goes from 1 to 6. All right, this case, j goes from 1 to 4. Nij, so that's kind of the j's side of control volume I, dot with f ij, right, and times sij equal to 0. Sij is the side of, so let's say this is ni1, and the size is si1, and this is ni2. It's a vector, and the length is si2, etc., etc. All right, and this interface flux is the only thing we need to approximate. Is this clear how it works in 2D? Any questions? Yes? That's a good question. Do we assume the flux is constant along the edge? We don't have to, because this is the average flux value along the edge. We need to approximate that. That's right. We need to approximate that, and during the approximation, we may think of this as a piecewise constant if you make that choice. But the derivation from the differential form up to here is exact, where Fij is the average flux along edge j, or it is equal to 1 over Sij, 1 over length of integral over this, let me say it's the Sij, f of u along this S. So it is the average over this line segment. And that number is what we need to, that vector is what we need to approximate. Good. Any other questions? That's a good one. So how do we approximate this? Any idea from the one-dimensional world? We are talking about how to solve conservation laws in 2D. Any ideas on how to approximate the average of the interface flux? The simplest idea. Right, so if we keep our simple idea of using a piecewise constant approximation in the two adjacent cells, so let me say this is the I cell. Let me draw my omega I plus 1, and let's say if we want to approximate this interface. If we keep these two cells to be, if we keep the U at the two cells to be piecewise constant, then we get a discontinuity here that is exactly the same as our one-dimensional discontinuity. If you zoom into a small region, in this area, again, we are solving a Riemann problem. We are solving actually a one-dimensional Riemann problem if you look at the direction perpendicular to the interface. All right, and this one-dimensional Riemann problem is exactly the same as our one-dimensional case because we are treating it as piecewise constant, and there is no variation in the tangential direction. All right, there is no derivative in the direction along the interface. So the only derivative is normal to the interface, and we can use our one-dimensional conservation law. We solve the one-dimensional Riemann problem. Yes.
So with that type of scheme, you would only have the average value of the entire cell to work with. Is that right?
That's right. I only have the average value on the entire cell to work with.